So we're recording. Just a quick refreshment on what we're doing here. Everything is on D2L. So everything that I'll do in class will be on D2L. You see, I hope you're familiar with how this works, right? So all of your assessments will be there under assessments, either as a Dropbox or a quiz. All of your course material, you should first look under news. The way the news is organized, you'll see that the newest stuff is at the top and the older stuff is at the bottom. But I won't delete anything. It'll all be there. And of course, you've also can go at any time to the content. And the content, I'll organize it by weeks. So everything to do with this week is there under a folder called week 1. And next week will be week 2, etc., etc. And so it'll just continue on like that. So that's how that is. I will, as you see from last lesson, we've had one lesson so far. And in the last lesson, I recorded what we did. And there's a video there. And so if you felt that you needed to review what we did, you could go back and watch that video if you wanted. You could also just go and look at the files that we covered in the lesson. So I'm trying to give you as much as I can to sort of get those things. So we were, and I think I've got this in a different window. Yeah, so we were discussing the first lesson and we didn't finish it. So I want to finish that now. Which was talking about the history of computers. And then after the history of computers, we'll talk about computers nowadays. And that should finish us for today. And then next lesson after this will be a tutorial where we'll look at some critical thinking exercise. So it won't be a lecture. So this will be finishing our lecture for today. So this is where we finished off, I think, last time. With the Van Neumann architecture. The Van Neumann architecture sort of has the idea of input and output and processing. And that is the model upon which computers have built since then. So Van Neumann came up with this architecture. You'll see that's in the 1940s. In the 1940s, Van Neumann came up with that architecture. And since the 1940s, we've been building computers according to the Van Neumann architecture. And so that means that we write our computer programs so that they'll work on the Van Neumann architecture. And so that includes this idea of fetch, decode, execute. We fetch from where? We fetch from some temporary memory. And so we've got a memory unit that's attached to actually part of that memory is actually in the CPU. We have some registers that are there. So we fetch some commands. We'll store our commands and our memory variables in the memory. And then we decode those into something that we actually have to translate the command from add this to a bunch of zeros and ones so that the computer can understand it. And the computer just understands the zeros and ones. Once we've got that decoded to zeros and ones, then we can execute the command. So we need all of these parts to make that happen. We need to have the memory unit from which we fetch it. We need to have a control unit, which is going to do the fetching. And we need to have the arithmetic logic unit, which is going to do the executing of the program. So based on this idea of this model, we're able to do this fetch, decode, execute, which means we can store computer programs in a memory, and then we can execute those programs. Does that make sense? And so the very first programming languages that were written for the Van Neumann architecture kind of look like this. This would be an assembler program language. The assembler program language didn't have much to work with, and so it had to actually specify the address where the code that it wanted to use, that it wanted to fetch. Where is that code? Oh, it's at memory address number 200. What are we going to do with that code? That code says add to R1, where R1 is going to be some other like a variable. And then so the computer programs work by sequence. That is, we run the first line of code, then we run the next line of code. So after we've done that, we're going to do the next one, and we're actually going to go and look at memory address number 201. And what we're going to do there, we're going to have a value of 100. And then we're going to add to R1, whatever's in R1, we're going to add this to it, and etc. And so the programs would be lots and lots of lines of code. Every little bit of memory address, we had to specify it explicitly. I shouldn't say I've never written assembler code. But the programmers had to do that. It was quite a lot of work to get any program to do anything because you had to do all of this. But that was the way the the computer was designed to make those programs, and the programs were designed to work on those computers. So that type of computer, from about 1950, the U.S. Census was run on computers built by Remington, as it says there, and also the U.S. presidential election was analyzed by computers like that, using this UNIVAC computer, as it says. And so it was using a programming language called AO, which is an assembler type programming language with code that looks like that one that we just looked at. So for example, you'd have a line of code that would say, add R1, R2, R3, where R1, R2, R3 would be variables which would be mapped to addresses in the memory. AO was an assembler type language. It seems that Admiral Grace Hopper was associated with that. And I think you might have seen her name also. We talked about her maybe in last lesson also. We're going to talk about her again in association with another programming language. So AO is a very simple programming language in terms of the tools that are available. You know, you have to specify the memory position, and then you have to specify what you're going to do with it. The programmer has to do that. Now later, nowadays, when we run our programming codes, we actually have a 3rd generation programming language or a 4th generation or higher. So for example, we're going to talk about COBOL in a minute. It was one of the 3rd generation programming languages. These programming languages run on your computer over an operating system. The operating system actually takes a lot of the work that was done here. It actually accesses the individual memory addresses and the other resources for you. All you have to do is give commands like store this variable, add this variable. You know, it's a lot. You're removed from it. You're a layer above it. It's easier work for us because a lot of the extra work, the actual input output is done by the operating system. So our operating system includes a basic input output system as part of it. Maybe you guys will study something to do with operating systems. There's courses here on operating systems that you might have to do. So storage on that very old computer, magnetic tape drives. So kind of, I don't know if you guys remember seeing magnetic cassettes of music. Right? And you start at the start and you go to the end. It's a serial form of reading and writing. That's how they used to store it. It's quite a cheap way of doing it. It's still used in some computers just for backup, but we wouldn't run a computer program using a tape nowadays because why? The problem is it's serial. What that means is if you've got something that you want to do that's at the end of the tape, you have to scan through the whole tape to get to the end before you can do it. And so we have much better ways of doing that now, which is direct access. That happened with the floppy disks and the hard disks. Nowadays, people aren't even using mechanical hard disks. And a lot of your laptops that you'll have a we call it a hard drive, but it's a solid state hard drive. It's called an SSD. And so no moving parts. So it's just all electronic, way fast. Boom, boom, boom. It's almost as fast as internal memory. And so that's a lot more expensive than tape. Tape's so cheap, but it's not as expensive now relative to other things. It's cheap enough that you can actually put it in a consumer-oriented laptop computer. A lot of you will have that. You'll have a computer with a SSD in it. Yeah, but so if you went back 30 years, you'd be using a tape. All right, or maybe 40 years, or maybe 50. So today's computers do a lot better than that. You know, not 2,000 calculations a second. Nowadays, computers are doing billions of cycles per second. And so that's really the power of computers, is they can just do things really, really fast. And so if you've got a simple task that you have to do many, many, many times, your computer's the way to go, right? I mean, it'll do it really fast for you. Dr. Grace Hopper, we mentioned her just a minute ago. She kind of came up with this language AO. She also came up with a programming language called COBOL. COBOL was a 3rd generation programming language that you ran over your other operating system. It was mostly run on mainframe computers. I mean, in the 1990s, 80s, there was a personal computer version of COBOL that was developed, but you know, who used it? Only university students, I think. So banks, governments, big companies, they use COBOL for their main business applications. So to take care of their inventory, to take care of their accounting, all of that would be done using COBOL. So you might say, well, was she a business person? Well, no, she worked for the United States Navy. Was the United States Navy care about about business programming. Well, I guess it's not really a secret, but if you're going to have a military, there's a lot of business involved in a military, right? They're buying things, they're moving things around. It is actually a very big business operation. So she defined this new term. She brought a new term into the English language, and I guess that went into the international language, which is this term called debugging. And debugging means to solve, remove errors from a program. And she actually coined the term because she would have to go into the computer and fetch moths and other large insects that had flown into the computer and had short-circuited the computer. And so the components were broken. And so then she would have to go and replace those components, and she would call that debugging, removing the bugs. Now we still use the term. We say debugging, but what we mean is removing errors from our program because we did a bad job writing it. We made mistakes. And there's two different types of errors that we debug. We have syntax errors, that is where we've written things using the wrong spelling or something like that. The program won't run at all. That's a syntax error. The other error that we could have would be a logic error where the program runs, but it doesn't do what we thought it was going to do. And that's because we made some mistake in the logic. You'll have lots of those as you go. As you become a better programmer, you'll be a good debugger. Now, the thing about debugging, as I mentioned there, you have tools that will help you in your debugging. You don't have to do all the debugging yourself. So your development environment will tell you where some of the errors are. And also you can do traces. We'll see that. So we can put some test data into it and then see what the program does and see if it comes out the way we thought it would. So we do a lot of that. We spend a lot of time as programmers doing debugging. But we're not pulling moths out of the computer. When we do a debugging now, what we're doing is we're finding those errors. The integrated circuit, the idea of the integrated circuit was that you can have billions of transistors on a single chip. And how's that possible? We use electron microscopy, graphy meaning to write, as opposed to scopy, which means to view. So you've probably heard of a microscope. Then there's this thing called an electron microscope. How an electron microscope works is instead of just reflecting light back into the eyes of an observer, what it's doing is it's shining, using very small electrons, to illuminate a surface in a non-visual way, I suppose you could say. And then you need a special device to read those electrons as they're reflected back. But the beautiful thing about the electron microscopy is that you can look at things down to almost the size of molecules. You can magnify things hundreds of thousands of times, as opposed to a light microscope where you're limited to maybe 1,000 times or something like that. So electron microscopy is a big use in engineering a little bit, but it was used a lot in biology and biochemistry, so looking at animal and plant systems. So electron microscopy, that's looking at things, or electron micrography, that would be drawing things. So using a similar tool to actually rearrange the molecules. And so if you can rearrange the molecules on a silicon dioxide wafer, you can draw integrated circuits that are so small they're almost at the molecule size, right? And so that's what we're talking about. We can get down to almost the molecule size of rearranging things. I think I've seen electron microscope of that IBM had showing individual metal atoms. So I mean, you know, that this is really, really cool stuff. And so if you can imagine how small those are, we've got a chip which is made out of silicon dioxide which has been doped with another metal oxide like germanium, and that gives you a semiconductor property, which means when you vary the electrical potential across it, you can get a difference between an on or an off gate. And so your on and off gate, that's how computers work. It's either on or it's off. If it's on, we say it's 1. If it's off, we say it's 0. And so that's what we're using in computers, zeros and ones. And so we can have billions of those zeros and ones possible on a chip like this. So we use those chips for memory, or we can use them for processing. But the capacity is huge. The chips are not expensive. I mean, you know, if you've got a standard chip that has been reproduced, they're not expensive if you only made one chip and it was a custom made chip, well, that would be expensive because it would take a lot of engineering to sort of get across. But what they do is they design a particular chip and then they reproduce it millions of times, right? So I mean, you look in your computer and you see on the front of your laptop, it says this is an Intel i7 inside or something like that, right? So this i7 chip has been reproduced millions of times. We all got an i7, right? Everybody, and so this chip has been reproduced many times. And so each time you produce one, it costs less, I guess, because you don't have to get to re-engineer it every time, right? We did it once, so we just have to keep reproducing them, and they're not too expensive. Many of these storage chips are way cheap. So you have a USB that you carried in your pocket. How much did you pay for that? I mean, some of them like 10 reals or something, right? So they can be quite cheap. Oh, I was feeling in my pocket and I've got the key to my car. Does that have a chip in it? Yeah, there's a chip in there. And this is actually kind of expensive. And I think the expensiveness of that is related to how many of them there are, right? So this is a Chevrolet car. There's really not that many of them. And also the thing that they like to rip you off, right? I think the actual chip in there isn't that expensive, but we need that chip because that chip communicates with another electronic device in the key thing. And if that chip's not there, the car won't start. It won't go anywhere, right? So a lot of us have cars like that. I mean, most of the new keys are like that. Anyway, so computers everywhere. We're going to talk about that in the next lesson. But just I wanted to say about that, we have been able to miniaturize these things and reproduce them quickly. Silicon dioxide is not expensive. Silicon dioxide is very, very common. There are things that are in the computer that are expensive and uncommon, but they're not used in very much quantities. So, you know, you got gold and platinum and rare earth metals that are required, but they're required in small amounts. And so that's sort of manageable. All right, so we have different units of measurement of memory and speed in computing. And so we talk about giga, mega, kilo. You've heard those things, right? So a giga is roughly equivalent to a billion, but we're using base 2 in computing instead of base 10. Base 10 we call decimal. Base 10 is how we count. And we've had that for a couple thousand years. But in computers, because we only got two numbers, 0 and 1, that's binary, two numbers. So we only got 0 and 1. And so everything is going to be based in 2. If you take 2 times 2 times 2, 10 times, 10 2s multiplied by each other, that would be 2 to the 10. That actually gives you a number of 1024. All right. So 2 to the 1 is equal to 2. 2 to the 2 is equal to 4. Right? 2 to the 3 is equal to 8. 2 to the 4 is equal to 16. You've seen these numbers. So these numbers become familiar to you, right? 2 to the 5 is equal to 32. 2 to the 6 is equal to 64. So we see these numbers. So basically, this is just equal to 2. This is equal to 2 times 2. This is equal to 2 times 2 times 2, etc. Right? That's binary, and that's how we do it. And so this is going to be 10 lots of 2 multiplied. And yeah, we could follow this down, and we'd see 2 to the 6 is 64. To the 7 is going to be 128, and then to the 8 is going to be 256, and then to the 9 is going to be 512, and then to the 10 is going to be 1024. Right? So you get the idea, right? And so we could continue on with these now. That would be a kilobyte. With a megabyte, what we're doing is we're taking that number 1024 and multiplying it by itself again, right? 1024 by 1024, we get megabytes. Gigabytes is kind of where we are in the consumer area of computing. So you guys have all got hard drives on your computer, and they may be SSD drives that are some multiple of gigabytes. Now, some of you might have decided that you need more than that, and so you got a terabyte, right? I mean, you can buy it. You can buy it at Carrefour, I think. So when I worked in a telephone company for a few years, and the hard drives on there, we would sell terabytes of data, and that was huge, man. You know, whoa, who's got terabyte of data? But and people thought that was so much, but that was kind of before I got it. Do we have to know that? Yeah, you do. So a good question. Do we have to know this stuff for the exam? Anything that's in the notes. If I take I do add things that sort of pop up in the back of my head. Sorry about that. But anything that's in the notes could be in the exam. Some of the segues that I take, yeah, maybe not. I don't write the exam, but so I can't say what's in the other teachers' minds, and quite possibly that won't be in the exam. But anything that's on these notes is fair game. That could be in the exam. All right. So this fellow Moore, he worked for the Intel company. You've heard of Intel. We just talked about Intel, right? Intel makes chips. And so they were making chips back in 1968, manufacturing chips. And he noticed that empirically, empirically means that you look at something, you must do an experiment or you must observe something. That's empirical evidence. And so he noticed that every couple of years, things just got cheaper. Basically, if he waited 18 months or 2 years, the amount of computer power, either in memory or speed, that he would get for the same amount of money seemed to double, right? So like every 18 months or every 2 years. And so he said, well, here's an informal law. This is what I notice. Every 2 years or every 18 months, what I get for my money doubles. That's Moore's law. And Moore's law seems to be true. It's still holding. There are some limits to it, particularly to do with the processor, and maybe I'll talk about that in a minute. Graphic user interface. The whole idea of the graphic user interface, really the first person to really do something about this in a big way, Xerox sort of did a little bit before the Apple guy. That one, Jobs, yeah. Xerox did a little bit before Jobs, but Jobs was really interested. He was an IT guy, but you know, he didn't have a degree like you guys are going to get. Just a smart guy that sort of ran into some people with computing. But what he was really interested in is art and sort of that kind of aesthetic thing. And so when he looked at the computers and got involved with that, he was thinking, well, couldn't we use the computer to do some other stuff besides just this boring accounting stuff and business stuff, right? And so you know, he and his partner sort of came up with this graphical user interface that you could draw things and make the computer sort of more relatable to people that were sort of not really interested in accounting and engineering and stuff like that. So he had a graphical user interface. The idea of the graphical user interface is it's intuitive. That is that somebody should be able to just look at it and sort of figure out what it does without having to look at a user manual. You know what I mean? And I think that's true for computing, right? You sit down your 5-year-old brother or sister or cousin to a computer and they'll poke away on the mouse, and pretty soon they figure out how to play a game or something without people having to tell them how to do it. It's intuitive. So that's what we mean by intuitive, is people can just sort of experiment around with it and figure out how to do it. And yeah, you'd say that. So I mean, you can look at that and you can kind of see what that does. You can see that that's a folder. You can see that that's probably a program or something, right? And so we have these icons. They make that intuitive as well. This one, by the way, is made by the IBM company. They had their own operating system that they ran on microcomputers. And you might say, well, some of you that know the history of IBM and know the history of Microsoft, you'd say, well, yeah, they had the operating system that was given to them by Bill Gates. Bill Gates gave them the operating system, which was MS-DOS. That's right. IBM bought from Gates, or anyways, they went into collaboration with Gates using the MS-DOS operating system on their first personal computers. But it wasn't a graphical user, it didn't have a graphical user interface. It was just a command line interface. And so when Apple came out with this graphical user interface, they responded and said, we'll build our own new operating system, which is not Bill Gates's operating system. We'll build our own new operating system, which has got a graphical user interface, and we'll put on new different computers that are different than all those clones. That's why you used to call them IBM clones. It's like every little manufacturing outfit in Taiwan started making computers that were based on the same architecture as the IBM. We called them IBM clones, you know, and they had all kinds of names like Xeno or whatever, you know, they're just strange names because they were not IBM. IBM did sell its own computers though. Anyways, so they came out with a graphical user interface. And then Windows, not to be beaten, came out with their own graphical user interface, which they called Windows. So Microsoft came out with that, sorry. And we still use Windows now on most of our desktop computers. But we've gone through a few versions of it. We're up to version 10 now, right? Is there another one after that? There's 11? You guys got 11 on your computers? Yeah, awesome. All right. So these are some individuals who are involved in that. Like you said, Steve Jobs, his partner Wozniak, Bill Gates, and his partner, Paul Allen. Paul Allen became the CEO of Microsoft when Bill Gates retired from Microsoft. Bill Gates still owns like, I don't know, a third of Microsoft or something like that. So he still makes money from Microsoft, but he doesn't have to work there, right? He just gets money that an owner gets. And so he went into philanthropy, I mean, giving money away to good causes or something like that. But the business goes on. Poor old Steve Jobs died, probably unnecessarily, but certainly too young. All right, so this is, who is this? This is Xerox, right? This is a Xerox mouse, I think. Stanford Research, 1963. So that mouse had a roller in it. So they were thinking about that before Apple. Then we came out with mice that look like this. They're kind of cool. The first ones had roller balls in them. And I still got some somewhere with a roller ball. But I mean, everybody now has got one with this, that's got this infrared thing going. And that's a little bit more precise. Sort of better to manage with. So that makes it intuitive. It's a lot better to work with, I think. Now down the bottom here, we've got this new topic. Sure, it should have a new headline probably. Ethernet is not about anything to do with a mouse. All right, so Ethernet is that blue cable that you got coming out of the back of your computer. That's Ethernet. Ethernet is for connections. Ethernet is a standard. It's a standard of a wire that's got eight wires in it. So there's 8 wires in their twisted pair. So 4 lots of twists. We use that for that's been standardized for local area networks. Basically, almost everybody's using that now. Now they didn't used to. I mean, when I first went into computing back in the 1980s, the first LAN that I worked with used a cable that had a wire in the middle and then a rep on the outside of it. So that was different than Ethernet. Ethernet's newer and it's better, but that's the standard now. We use that. You've got a Ethernet port on the back of your computer or your laptop probably. Okay, so why is that there? So the next slide goes to internet, and Ethernet, I guess, could be related to internet because Ethernet allows us to have networks. How does that relate to the internet? So here we got a network in this room. We could have a network which was just this room. And then we could connect this room to the rest of this building. And maybe we could connect it to the entire campus. And if it was one location like that, we'd call that a LAN, local area network. Now, that's how that happens. We've got this Ethernet cable that connects to a telecom box, we call it, in one of these rooms. And then we have fiber cable. You know what I mean by fiber, which is optical fiber that's using light instead of electricity. That's the same as what you have coming into your house from Irido, is giving you a fiber optics so that you can have faster internet. All right, so fiber optics is going to have faster, broader band, will carry more data more quickly than the Ethernet cable. The Ethernet cable's fast, but fiber would be more fast. So we would use fiber between these rooms and there's a cabinet down the end of the hallway, which basically concentrates. It's got a switches in there, and the switches gather data from all of the rooms. And actually, there's a switch in each one of those cabinets as well. But then that goes down to a room at the end of building 3, and that room has routers in it and has a connection to Irido, and Irido gives us our internet. So we get the internet from Irido. They're an internet provider. They allow us to connect to the rest of the world, right? And we have to pay for that service, of course. But that's what we mean by the internet. So we have networks. If you have a network of networks, networks connected together. We call that an internet. We also have a term which we call the internet with a big I. Capital I, the internet, is the thing that we talk about when we say, you know, when you're doing your social media and that kind of stuff, and you're reading things from around the world. That's the internet, as opposed to an internet, which could just be any bunch of networks connected together. So the internet has a history that's a little bit long too. Basically started with some ideas from these people back in 1960s. How could we connect networks together? And basically a bunch of universities and the US government, they seem to pop up all the time. US government, ARPANET, and the DoD, which is Department of Defense. So US military, they came up with a network that involved a few of their outposts. And then actually the next step after that was a bunch of universities, mostly in the west of the United States, started communicating with each other. When the universities started communicating with each other, they thought it would be really good to have some kind of messaging. And so some of these guys developed an email program. And so that was kind of one of the first uses of the internet. Now, the internet was really basic then, right? So back in the 70s, it was really basic. It was just a few universities and the US military, and they're just using it for sort of sending messages around. Then in the 1980s, as it says, the internet with the capital I emerged for the rest of the world. And so telephone companies started giving access to it. So the internet, the first time I had an internet connection, that would be around then, maybe 91, 92. And that internet connection, yeah, it had a command line interface. It didn't have a GUI interface. So the GUI interface came with this idea of the World Wide Web. The World Wide Web is built on HTTP and HTML. HTML is used to build web pages. And so that's when we got the thing that we call the web, which is sitting on top of the internet, we have web pages, websites everywhere. And that is HTML and HTTP. So that didn't really get going until, as you see, 1993, Mosaic was launched on the web. And then it went pretty quickly from there. So after Mosaic, like almost the next year, there was this thing called Netscape. By 95, many people were using Netscape. And then Netscape was replaced by Windows, had their Internet Explorer. It sort of captured a lot of the market. And then along came these other ones, right? So Firefox, yeah, there's Internet Explorer, Safari for the Apple universe, and Opera worked on both of them. And then, of course, Google Chrome. And a lot of us use Google Chrome now. So Google, as opposed to Google Chrome, was really a search engine. So the idea of that is sitting on top of all of these web pages. What if we could sort all those web pages out and provide easy access to any of them for anybody who wanted to know where they were, right? That was the idea. It started out with these guys here. No, not him. Bill Gates. Bill Gates just said that he though he was a really smart guy, he didn't think that you're going to need to have very big computers back in 1981 because they couldn't imagine what they would use them for. Like in 1990, what did we think a phone was, right? We were really, really excited that we were getting smaller and smaller phones. You know, the phones just kept getting smaller and smaller. And so eventually we had this like the little Nokia 3120 or whatever it was, you know, it was kind of, we thought that was it, man, that's the end of it, right? And then we realized, well, you know what if we put some other stuff on the phone, right? What if we could have a bit more than just a SMS message? What if we could have some sort of graphics going on? And then explode out, right? We're watching movies and, you know, we got social media. You know, now it does a lot of things. We're doing our GPS navigating on them, you know, so it's no longer just a phone, right? And so those guys wouldn't have had any idea that a phone is going to be like a computer in your pocket. They just thought it would be a smaller phone. And yeah, so I mean, it did go pretty quickly. They've got another message, Opera Mini, yeah, very nice. So these guys here, they look kind of young because they were kind of young. So they're at Stanford University. Stanford University is in California, in the area of San Francisco. The thing that makes Stanford University of interest that you might care is there's a lot of really rich people that give it endowment. They do that. That's good because that means that they can pay a lot of money to their staff. So they have really expensive courses and staff. The other thing they have is a lot of really rich people go there looking to find smart students who will have some kind of engineering idea, which they'll turn into a lot of money. And of course, so these guys there, they're really smart people. And then some really rich people come along, give them some money, and, you know, let's work together and make more money. And how are we going to do that? Well, what if we had this system which could sort all of the pages on the internet so that it was easy for us to find them using just a search sort of thing? And so they developed the technology to do that. They called it backrub, which didn't sound all that cool. And then they came across a different idea. There's this word called Google. Google, not Google, but Google is a one with 100 zeros after it. So in other words, a really, really big number, which would be like, how many pages are there on the internet? Well, we hope one day a really, really big number, and our really cool product will allow you to get to any one of those as fast as you want. So sort of, maybe. So that made them a lot of money. And of course, Google went and bought lots of other companies and stuff like that. So I'm using this mobile phone. When I bought the phone and I turned it on, and I had to create an account, right? I had to have a profile on the phone. And of course, that's all Google, right? I mean, so it's Android, but Android is owned by Google. And so I had to have a Google account, and so Gmail and all that other stuff, right? And so why do they care about that? Okay, so every time I do a Google search, every time I buy something, every time I speak, you know, they're listening, the phone is listening to me. It's gathering information about me. Why? So it can sell me stuff, right? And every time it goes to sell something, it charges the people that, you know, for advertising. So you become the product, as it were. So they made a lot of money out of that. So what they can do is they can go around selling time, space and time to advertise products to other people. Well, you notice this happens, right? You're talking in the room about something. You know, I really like to get a new, I don't know, X. And then next day on your Google, you've got an advertisement for it, or maybe on Facebook. You know, they kind of work the same way. And it's like, oh, isn't that, how could it read my mind? Didn't read your mind. It's able to, it can work with sound, right? You can talk to your phone and tell it to do stuff. So just like that, it can work with your voice. And there's a summary of those things. Most of you guys were born after the start of the second column here. So there's a lot of stuff that happened in computing since you guys were born. There's a lot of stuff that happened before, but you know, there's a lot of stuff that keeps happening. Right? Anyways, I think that's just about the end of our lesson. Oh yeah, so just a review on this. Let's look at some special people in computing. This one is Steve Jobs. Died too young, died of cancer. Sorry, Steve. Charles Babbage, he made the mechanical calculating device, right? The Babbage's engine, Babbage's difference engine or analytical engine. So long time ago, right? 1980s, sorry, 1830s. Turing, remember what he was important for? He actually came up with the Turing